Hi everyone, welcome to the second episode of the tutorial on variant calling using Freebayes. In the first episode, I showed how to call variant using Freebayes from a single sample. In this tutorial, we are going to call variant from multiple samples. So just make sure to watch the first episode if you have not done so. So take note of that. So again, I will show the original tutorial. There's a page and I'll leave the link to this page in the description box. So we are going to follow everything here, the variant calling part. That's what we are going to do. So take notes. Now for this tutorial, I've already prepared the materials. So just make sure to download these files, these two files. We will add additional command, but these ones are the core ones. So make sure to get them. So the download links are in the description box. So for this tutorial, if you want to follow, you need to make sure that you have a Linux system and you should also have Mamba or Micromamba installed on that system. I have tutorials that show how to install Mamba and Micromamba. So check the description box, you'll find the links to those videos. You will use Mamba or Micromamba to install the tools. All right, so that's what we are going to do. So let's open our terminal and then start the exercise. All right, so we will first create an environment and install the tools. So I'll say Mamba create -n and then I'll say variants. And then I'll indicate the tools. Now before I even indicate the tools, I will need to indicate the channels. So I will indicate my channels here. So I'll say -c, bioconda -c, underforge, and then -c, defaults. I'll indicate all these three channels and then I'll indicate the tools. So the tools, I have some tools, VWA, and then Freebayes. So these are the tools we will use. All right, so let's execute this command to install the tools. Now I'll type Y to confirm. So after doing that, Mamba will download all the necessary packages and then configure them for us. All right, the tools have been installed. So let's activate the environments. So I'll say Mamba activates variants. Nice, the environment has been activated. So let me do an ls again to check my files. So these are my files. All right, so now we can proceed with the exercise. All right, so what we are going to do next is to download the example data. So the download links can be found in this file. So I'll just do a cut. So cut download links.txt. So I have the links here. So I have my reference sequence, and then these are the reads, the FASTQ files. So we have 3 samples here. All right. So that's how I'm going to do it. I'm going to download them. So I will say cut download_links.txt, and then I will bring a pipe and I'll say x-axis, and then I'll say -p, and I'll say 4, and then I'll say -i, and then I'll say wget -c, and then I'll bring a quotes, and then another quote after the curly brackets. So I'll close the curly brackets, bring another quote. So this becomes my final command. So x-axis is used to execute commands from standard input. So here the cut command is supposed to display the links, but what we are doing is that we are feeding the links to x-axis, and then x-axis will execute wget on all the links and then get the files for us. So that's what this command is about. And by the way, I have a separate tutorial that shows how to use the x-axis to download multiple files. So if you want a detailed explanation, check the description box. The link to that video is there. All right, so let's execute this command to download the files. All right, so the files are being downloaded. So let's wait for everything to get done for us. All right, the files have been downloaded. So let's take a look at them. Let's do an ls. We are going to find the file there. So we have our FASTQ files and we also have the reference sequence. So I will say ls star fq star. So this will list just the FASTQ files, and I also have ls hg19 star. This will list just this one for me. So this is the reference sequence. It is zipped, by the way, so we will decompress it later on. And then we also have the FASTQ files. We have 3 samples here. These are paired and read, so that's why we have 6 files. So each sample will have 2 files, forward and reverse. So we have R1, R2. All right. Now we need to organize the files. So I'll create a directory and then move the FASTQ files in there. So I'll say make the FASTQ. And then I'll move all the FASTQ files. So I'll say mv star.fq star.gz. And I'll specify the directory, which is FASTQ. So here I am moving all files that have this pattern in their names, and then ending with .gz. So I'll execute this command. So now if I do an ls, I'll see my FASTQ directory. When I ls into it, I'm going to find my FASTQ files. So I have them here. All right. Now let's also process the reference sequence. So first of all, I'll say make the ref, and then I'm going to do this. I'm going to unzip the reference sequence. It's now .gz, but we need the decompressed one. So I'll say unzip, and I'll specify the file. So I'll execute this command. Now if I do an ls, I'm going to find it there. So I'll move it to the ref directory. So I'll say mv hg19, and then we have the other names, and then I'll say ref. So that has been moved. So if I do an ls into ref, I'll find the file there. Nice. So now we have processed the file. So we are ready to start the exercise. So let's clear the screen and continue. All right, so let's do an ls to check our files again. Now with the original tutorial, let's just go to that page. They start with quality control, but I'll skip it because I have already covered that in the first episode. So just take note of that. So I'll move straight to the read mapping side. All right, so we will use BWA to do this. So let's get back to our terminal. And so before we perform the mapping, we need to first index the reference sequence. So the reference sequence can be found in the ref directory. So we will use BWA to index it. So I'll say BWA, and then I'll say index, and I'll say ref slash, and then I'll specify the file, and then I'll execute this command. All right, so indexing has started. So let's wait for everything to get done for us. And also with the tutorial, you can also use your own data. Once you follow these steps, it will be easy for you to rerun it using your own data. So just take your time and then follow the steps. All right, indexing has been done. So let's clear the screen and continue. So if I do an ls into the ref directory, I'll find some additional files there. So in addition to the first A file, you'll also see these ones here. So once you see them, that means everything is fine. All right, so now we can proceed. So we have generated the index files. So we can now map the reads to our reference sequence. All right, so let's take a look at our FASTQ files again. So I'll say ls FASTQ. So we have the files here. Now, the files we have here, we have 6 files. So we are dealing with paired and read. So each pair will belong to one sample. So in total, we have 3 samples. And so if you are dealing with multiple samples, like in this case, then it's important to also factor in some information. Okay, some key information that will help you to write scripts to automate the process of mapping. And I've already covered an entire tutorial on that. Check the description where you'll find a link to that video. So if you are going to write a script to deal with multiple samples, then there are things you have to factor in. You have to factor in the names, and this is where a good naming convention comes in handy. And if you are dealing with paired and reads, you also have to factor in the pattern that you use to differentiate between the forward and reverse. So in this case, we have this. And then we also have this for forward and then the reverse. And you also need to factor the file extensions. So here we have .fq.gz. So we are going to use the script here and then supply all the necessary information, and from there the mapping will start. So again, let me repeat, you need to have the name of the file or the sample. So we have father, we have mother, we have proband. You need to also get the sequencing type. Here we are dealing with paired and read, so you need to get the name that is used to distinguish or differentiate between the forward and the reverse. So here it's R1 and then R2. Some also use 1 and 2. So here, if you're using your own data, just make sure that you identify the names that are used to differentiate between your files, I mean the paired and reads. And then you also need to look at the file extension. So here, the file extension is going to be the .fq.gz. So after the sample name and then the pattern that's or the name that is used to distinguish between the forward and reverse, you can specify all other information as the extension. So these are the things you need to factor in. So just make sure that your files have been named like this one here. They should have the same format as this so that you'll be able to use the mapping scripts here. All right, so let's open the mapping script. So I'll use Nano, but you can use any text editor as well. So let's open it to supply or to enter some information. So I'll say nano mapping.sh. All right, so that has been done. So the scripts, let me also open it. I think I've opened it somewhere here. Let me check. Okay, I think I have it also here. So the commands are just when you scroll down, you see all the commands there. So we are going to supply all this information here. So let's go to the command line. We'll do that here. Let me just clear this. This is not supposed to be there. All right. Yeah, now it's clean now. Okay, so let's start. So first of all, I indicated the pattern or the name used to distinguish between the forward and the reverse. We are dealing with paired and read. So for this data, let me just do this. It's R1 for read 1. So you put them in quotes. And then read 2 is R2. You also put it in quotes. Then the file extension is .fq.gz. We also put that in quotes, double quotes. And the platform here, it's Illumina. So I'll specify that here. And then we also need our reference. So the reference file, or the reference sequence can be found in ref/aj19 underscore chr8.fa. And then the fastq dar is what? Fastq. And then threads 6. So this is what we have. So with a ref, you need to specify the part which has the fasta file. So this part here also has the index files. And the fastq dar, the directory which has the fastq files. And then we also have threads. So the threads here, I'm using my normal laptop, that's why I've specified 6. But if you have a high computing power, then you can increase it to 8, 10, or 12, or whatever. So it depends on you. So just make sure that you have supplied all the information as it is. Okay, and if you are using your own data, just make sure that you supply the appropriate information here. All right. So in principle, this script can be used on your own data. So that's why I'm showing you the information that you need to specify so that you can use it. All right. So let's proceed. So we can now proceed with the exercise. So let's save the changes and then exit. So let me just go over. Let me just take you to the other script which has the one for the single sample. I think we have to look at that also before we proceed, for those who just joined or those who are watching the video for the first time. All right, so this is the scripts that I'm using. I've basically expanded it. So in the script, we have our mapping, which we will do, and we also have this one here. So we've already done the indexing. And so what we need to do is to also specify some information here, which we will be doing that automatically because the script has that command. So in the process of the mapping, we need to indicate read groups. So we have ID, name, and then we create the final read group information. And then we perform the mapping with BWA. That is here. And then we can also check the mapping statuses, but I've skipped that in the other script. And after that, we need to process the BAM files. So the processing is done here using all these steps. And then we finally call the variant. So it is all these steps that I have automated. Okay, so they are all in the mapping.sh scripts. And then the only thing I did was that I also wrote a loop. So the loop would take each of the samples and then map them, get the raw BAM file, and then process them. And then we will finally call the variant. So I've basically automated the process because we are dealing with multiple samples. All right, so that's all that you need to know about this script. So once you understand this, then it becomes easy for you to also understand this. So the only difference is that with this script, the automation has been done, and then the automation, I repeat, the automation will take off after all the information has been supplied, and then you can proceed. So that's basically what we have done here. All right, so let's exit and save the changes, and then we can now run the script. So with the run of the script, we first need to add execution right. So I'll say chmod +x, and I'll say mapping.sh. So if you're going to execute, for one of the ways to execute the scripts, you will need to make sure that you have the execution rights added. But there's another way that you can execute the scripts without having to add that. So I'll show you all of them, by the way. So let's execute the script to map our reads. So the first approach is use // then supply the file name like this. So if you're using this approach, then you need to make sure that you have added the execution rights. That's what I've done here. And the second approach is to just call bash and say mapping.sh. So this also works. So any of those approaches will work for you. But I'll use this other approach, the first one. So I'll say // and then I'll say mapping.sh. So I'll execute this command now. All right, so once I do, BWA will start its work. So this command may take more than 5 minutes, depend on your computing power. So just be patient and then wait for everything to get done for you. All right, mapping and processing of the BAM files has been completed, so we can proceed. So let's clear the screen and continue. All right, so let's do an ls. We are going to find this BAM directory. So let's ls into it. So I'll say ls BAMs, and this will display the BAM files for me. Now the BAM files, some of them end with .raw.bam, some of them end with .dedupe.bam. So the .raw.bam file, these are the raw BAM files. These were generated after the bwmm command was executed. So it is these files, the raw.bam files, that have been processed to give us the .dedupe.bam file. So these ones here, they are the final files, the analysis ready files. So they have the duplicate reads removed. Now let's display the raw BAM file. So I'll say ls bams star.raw.bam. So this will display the raw BAM files. Let's also display the dedupe.bam file. So I'll say ls bams / star.dedupe.bam. So these are the final BAM files. So we are going to call Freebayes and then identify the variants from these samples. These are the final BAM files. These are 3 samples here. All right, so that's what we are going to do next. Now, if you are going to use Freebayes to call variants from multiple samples, then there are 2 approaches you can use. You can either call variants from the individual samples and later merge the VCFs, or you can supply Freebayes with all the samples at once, i.e. the BAM files. So in this tutorial, we are going to supply Freebayes with all the BAM files at once. So before we do that, we need to do some preparation. So I'll first generate an index file. So this index file is the .fai file. So we have to use some tools to do that. So I'll say some tools and I'll say with X, and then I'll supply it with the reference sequence. So I'll say ref/ag19. Yeah, there's the file. So let's execute this command. Perfect. So that has been done. So if I do an ls into the ref directory, I'm going to find that file here. So there's a .fai file. All right. We also need to store the path to the files, the BAM files here. We need to store the path to a text file. So to do that, we need to display and then redirect the output to a file. So we'll use the same command here and then add something else. So I'll say ls bams / star.dedupe.bam, and then I'll direct to an output file. So I'll say bam.list. So now if I do an ls, I'm going to find the bam.list file here, and then I'll say cut bam.list to display the contents. So I have them here. Nice. There is something else we need to do. So let's clear the screen and continue. Let's do an ls. Let's display the bam.list again. Right. Now we are going to create a directory called VCF. So I'll say make the VCF. Nice. Now the preparations are complete, so we can call Freebayes. So I'll say Freebayes, and then I'll say -f, and then supply it with a reference sequence. So that would be ref/ag19, etc. So there's a reference sequence. Now we have to indicate the BAM file. So I'll say -l, and then I'll say bam.lists, and then I'll say --vcf, and then I'll say vcf/variants.raw.vcf. Perfect. So this becomes our final command. So let's execute this command. All right. So Freebayes is working now. It will take some time, so be patient and wait for everything to get done for you. All right. Freebayes has completed this work. So if I do an ls, I'll find my vcf directory. I can ls into it to see my vcf file. So this vcf file here, I name it raw because normally after variant calling, you need to process the vcf further. So this becomes the raw vcf and then you can process. So with the processing, you can remove low quality variants, so SNPs and indels. You can also decide to subset, maybe get variants for a particular sample, or you may want to also get variant for a particular chromosome, or you can also filter based on quality etc. So there are a number of things you can do here. So those things, I've covered some of them already, and I'll also cover some of them later on. But for now, you just have to learn how to call variants. So after calling the variants, you can use tools like BCF tools, VCF tools, etc. to process the VCF further. And then you can also use other downstream analysis tools to analyze your data. For example, after variant calling, you can perform variant annotation. You can also look at variant effects. So you can also do your GWAS analysis, etc. There are a lot of things you can do here. So it depends on the questions that you want to answer. But everything starts after you have generated your VCF. So this is why this tutorial comes in handy. So learn this to generate your VCF files, and then you can proceed with your analysis. Now, if you're interested to learn how to use other tools like BCF tools to generate VCF files, so let me just say to call variants, then you can check the videos in this playlist.